To be,
Oh, stop
I
it.
go put a.
I think it's time. Uh, First thing I want to ask is because we are going too slow at the moment, I want to ask our three students who are here tonight if they're willing to stick around until 9:30, go an extra half an hour tonight and probably for the next couple of weeks. The alternative is we have a review session scheduled about 4 weeks from now, and we can cut into that if people would rather wind up right at 9 o'clock. So what do people think? Don, John, Carrie?
How about 9:15? I start pooping out, and I'm finding that we're getting into the stuff that I don't know very well.
Okay.
I, I'm flexible, I stay as long as I can. If I drop off, I'll let you know.
Okay. We will go just a little bit long then tonight, and then probably in a few weeks, instead of having a week only to review chapter five, we'll have a week where we finish chapter five and then um, ah, here we go. We'll
Whatever.
go where we finish where we finish the chapter on electronics, and then have a shortened review. So okay, 9:15 tonight, and then we will see what we can do about going a little bit faster. So without further ado, now that I put all of the weight on him, I'm going to turn it over to John, who is going to finish up on radio building blocks. So take it away, John.
Okay, see if I can share properly. Oh yeah. Uh, there we go. There they are. Okay. I think this is where we were. Amplifiers. Um, let me adjust things here a minute. So with an HF rig, most of the ones, the most you'll get out of an HF rig usually is 100 watts, sometimes 200, sometimes 20. So a lot of people put an amplifier after that because legally you can go up to 2,000 watts, I believe, with your HF privileges. Or with the general privileges, actually, you can go up to that on the VHF and UHF. Anyway, so amplifiers. So we have a section on amplifiers. They've been around as long as ham radio, I think. HF operators use amplifiers to boost their signal when conditions are poor. And some bands, they're more prevalent than others. On the very low bands, they're noisier, so you tend to use amplifiers like on 80 and 160 at least. Now up on 10 and that, they're not quite as, the bands aren't as quite as noisy. Um, so classically, they were vacuum tubes. Now there's a lot of solid state HF amplifiers. Usually UHF and VHF are already solid state amplifiers. Um, the thing with the tube amps is they're a little more tolerant of bad bad antennas and high SWR in that the vacuum tubes. When you get to the solid state, you have to have it tuned up right. So a lot of the solid state amplifiers have a built-in tuner. Um, the efficiency of a amp. Now this is for the test. The efficiency of an amplifier is defined by the output power divided by the input power. Um, so the RF output divided by the DC input, which means all the losses in the amplifier are accounted for in that calculation. Power in over power out. They're also called linears because they they're a linear amp. Let's see, I think we get into that right here. So a class A is a linear, the lowest signal distortion, least efficient because class A's pass the entire sinusoidal input and conduct 100% of the time. Linear means, of course, the gain is constant, no matter how loud your signal is. The other one is Class B push-pull, a pair of amplifying devices, each acting during complementary halves of the signals cycle. Good linearity and good efficiency on these, because each one of the pairs only conducting half the time, so it's a little easier on the components. Then midway between A and B is not linearity is not as good as A, but efficiency is improved. Um, and then the last is the C class, which are not linear at all, but they're used for CW and FM because neither one of those, um, you don't care about the linearity because it's coded either in the CW as on and off or in the FM by moving the frequency, but the amplitude of the signal don't matter on those two, so that you can get by with a Class C. A lot of your amplifiers for the UHF and VHF bands are also C. They're just more efficient. You can get by with smaller parts. Some linear amplifiers can be operated either as Class AB for sideband or C for CW. Oh yeah, I don't have one of those. Transceivers often include a delay in the keying circuit timing so that the changeover relay is completely switched off before the transceiver is allowed to apply any RF output. So typically transceivers used a relay to switch between to switch the power in and out, and that's where this hot switching. If you're passing a lot of power while you open those contacts, you'll draw an arc, and it's not good. It'll sound noisy and wear out your relay real quick. Can destroy the relay and other devices too, and yes, and other things that are driving it as well with all that noise. Did that work right? Let's see. Didn't skip that. Okay. Now this one will be on the test too. Set the band switch to the desired frequency, of course. Well, I did two again, didn't I? Apply drive power to the amplifier while adjusting the tune control to obtain minimum plate current, called dip. So these two, the tune, you have to dip. You want so you turn on your transmitter and you key up the amplifier, and then you adjust your tune control for the plate current that you want. Usually there's a maximum plate current that you're trying to stay under. Adjust the load to obtain the peak power, and then continue adjusting until the max output is obtained. So what they mean by that is then you should, after you obtain your peak power output on the load, you go back and retrim up your tune, then you go back to the load there for a final tweak. Avoid exceeding maximum plate current, and that'll burn up your tube. Input power to the amplifier may also be adjusted during this process. So yeah, you'd probably want to start at a low power till you get her tuned up. Tubes can be destroyed by applying too much drive power. Modern amplifiers have protective circuits. We'll count on that. Similar cautions apply to solid state amplifiers with power transistors that can be destroyed with excessive drive power, for sure. Some amplifiers generate automatic level control, ALC. When you get a rig, you'll see that all over it, and you're like, "What am I doing? What's that?" What do you care about that? Well, just it's only applicable if you're driving an amplifier. This can be connected to the transmitter, so most rigs have a input for the ALC, or an output for the ALC, excuse me. Check both the amplifier and transceiver manuals to be sure signals are compatible, and so you know how to use the ALC meter reads. It's it's a control voltage that is exchanged between your rig and the amplifier. Now neutralization. Now this applies to tubes mostly. HF amplifiers can self-oscillate because of positive feedback in an amplifier tube. Self-oscillation creates spurious output signals and may damage the tube or amplifier components. The technique of preventing self-oscillation is called neutralization, done by creating a negative feedback, small variable cap, between the amplifier's output and the inputs. Sometimes mine's just a little wire that runs by the tube that you adjust. So that's the end of that. The self-oscillation has to do with, it's a tube phenomena where the plate and the components act as a little capacitor, and that acts as the feedback path. Okay, here's the questions. What is the effect on plate current of the correct setting of a vacuum tube power amplifier's tube control? What effect on plate current of the correct?
Pronounced dip.
Pronounced dip? Okay, we'll see. Yep, pronounced dip in the okay, in the plate current. All right. What is a reason to use automatic level control with an RF power amplifier? To balance the transmitter's audio frequency response, to reduce the harmonic radiation, to prevent excessive drive, to increase the overall efficiency.
Charlie, hey?
Which one?
Charlie, because you don't want to wreck the thing.
Oh, yeah, exactly. That's the only one here that kind of, if you know what the ALC does, that's the only one that really matches it. It kicks back the drive. It's a little feedback circuit. What is the correct adjustment for the load or coupling control of vacuum tube RF power amplifier? What is the correct adjustment of the load or coupling control? What these are a little a variable capacitor, and they're little tank circuits that you're adjusting in the output of the tube or on the input of the tube. Okay, so what is the correct adjustment for the load? Minimum SWR, minimum plate current without exceeding maximum allowable grid current, highest plate voltage with minimum grid current, desired power output without exceeding maximum allowable plate current. Well, there's minimum plate current, desired output without exceeding. Those two look pretty good, B and D to me. Any guesses?
D delta?
Yeah, that matches it better. I do believe. I can't
Because
see.
there's not necessarily a one-to-one relationship between the voltage and the power, right?
Right, yeah, they're pretty nonlinear. And C here, no. Never mind. Yeah, D's the only one that really applies, isn't it? Okay. See it? No, wait a minute. I flipped on it, didn't I? We were back here. D, desired power output without exceeding. Yeah. Yeah, because there was one. B almost fits, but D is the correct answer because of the output power is what you're really adjusting for there. This one, what is the purpose of delaying the RF output after activating a transmitter's keying line to an external amplifier? To prevent key clicks, to prevent transient overmodulation, to allow time for the amplifier to switch the antenna between the transceiver and the amplifier output, to allow time for the amplifier power to reach operating level, Oh, here comes another one.
Yeah, it should be Charlie.
Should be Charlie. Yeah, it's a time thing, isn't it? It isn't that you're waiting for it to reach output level. It's just it's you want the switch operation to be completed before you put the power to it. See, it is. What is the purpose of neutralizing an amplifier? To limit the modulation index, to eliminate self-oscillations, to cut off the final amplifier during standby periods, to keep the carrier on frequency. Yeah. Wow, I already did. I did it again, didn't I? Oh boy, like that. Eliminate self-oscillations. Um,
Yep.
it's all about oscillations. Is what you're doing there. It um, these RF circuits tend to self-oscillate at their natural frequencies, and that's what's going on here. Which of these, boy, oh boy, I gotta get off of that mouse. Which of these classes of amplifiers has the highest efficiency? Class A, Class B, Class AB, Class C. So, um,
I'll take a shot, say Class C.
yeah,
Yeah.
yeah, it's the only one you can't really use with AM or sideband because the amplitude of the signal is affected. The nonlinearity will get to you, so you can't use a Class C for those types. Um, but it's the highest efficiency. That linearity is sort of that costs you. In a Class A amplifier, what percentage of the time does the amplifying device conduct? And this is the answer to the previous one too. Um, what percentage of the time does the amplifying device conduct? Which is power, right?
Well,
100.
hey,
Yeah, it is 100%. 100%. Yay.
Which is why it's not the most efficient.
Right. It's always on. And if you ever see a C, it's just almost looks like square waves. Sometimes the output of the C, they just turn it on and turn it off. And it's that in between time that really is expensive to the devices. Um, anyways, how is the efficiency of an RF power amplifier determined? Divide the DC input power by the DC output power. No, divide the RF output power by the DC input power. Multiply the RF input power by the reciprocal of the RF output power. Add the RF input power to the DC output power. Okay. Did you guys follow that? Anyways, it was
it's Bravo.
Bravo.
bravo it is. Yay. Moving right along. Which of the following modes is a Class C power stage? I'll say it. Is a Class C power stage appropriate for amplifying a modulated signal? Which of the following modes is a Class C power stage appropriate for amplifying a modulated signal? And there is only one answer there. I would say D is wrong. But this is
I think it's B Baker, B
yeah,
Boyle.
yeah, the AM and the sideband of the amplitude of the signal varies with the amplitude of the audio signal. So but C type it's nonlinear, so you wouldn't be able to pass that information on the sideband or the AM, only the FM or the CW. B it is. And that's the end. That's who wrote it. And I am done. I can eat my sandwich.
Good job.
Well, thanks. I had to get momentum going there. Boy, when I first started reading, it wasn't flowing well. Got to warm up before I check in here, I guess. So Wes is going to go on with digital modes, I believe, except he ran away.
We're not doing 5.5 HF station
No,
installation?
I'm right here. Actually, we have another whole slide presentation that's still part of chapter 5. You or
Wait,
me,
Oh,
John,
okay.
take your pick.
oh, I thought you were doing the digital one. Oh,
Yeah, but there's another thing for chapter 5 also. All right,
HF
let's see
station
here.
installation.
I will just, all right, I will just go ahead. I will just go ahead with that. Um,
huh.
bear,
So there's another slide deck, huh?
yeah, bear with me just a second here.
Sorry. I wonder where it went.
Five's got a lot of stuff in it.
Part one of two. Okay. Yeah. I thought it was simple. Hmm.
All right,
That's why I was making good time, huh?
let's see what I can do here. Uh,
I'll
bear with
go.
me just a second.
Yeah, I'll go looking for it here. Hmm.
All right.
Chapter 5.
All right, so let's see here.
Still looking. Hmm. There it is.
All right, I think this is the right one. Can people see a slide that says linear means?
Yep.
Okay, I'm going to do something real briefly and then go into the next section of the official slides. I want to talk about linear and nonlinear for just a minute here, and I want to go very quickly because John's been throwing those terms around, and some of you might not understand what that means.
Yeah, there wasn't a good picture on that slide deck at all.
Um,
Not
in
right.
terms of really strict definitions, if you have a circuit with an input and an output, linear means that the output is an exact replica of the input. And the only difference is the amplitude, how strong it is. Radio definition, the definition we use in amateur radio is basically that a linear circuit does not add any new frequencies to the signal that it is processing. Um, and we stretch the strict definition a little bit because we use filters to filter out signals by frequency. Um, and we consider those to be passive filters, which don't have any active components. In other words, they're only made of coils, capacitors, and resistors are also considered linear because they don't introduce any new frequencies into the radio signal. So let's see here.
Okay,
So
I found it.
nonlinear means that the output of a circuit is not an exact replica of the input. And in radio definition, that means that the circuit adds signals that are at frequencies not in the input. Um, and these added components are called distortion. Now, every active circuit with tubes, transistors, and so forth is going to introduce distortion because the electronics just are not perfect. But most circuits are good enough, for instance, you can hear people with good ears can hear about 1 or 2% distortion in audio signals. And if you're listening, for instance, to the speaker on a handy-talkie, you can tell that a person's voice sounds somewhat unnatural, and that's because of the distortion in the audio amplifier and in the speaker itself. Um, or sometimes when a cell phone connection is poor, it is uh, it is caused by distortion. So um, anyway, I want to talk also about the types of distortion. I'm not sure how much of this is actually on the exam, but we're going to throw around different we're going to throw around some different terms, and this is getting a little bit ahead of 2 weeks from now, but it may help make things clearer from what we've been talking about. The types of distortion, the first type is harmonics. If you have a signal at a frequency, then the multiples of that frequency are the harmonics. So, if you have a signal at, say, 1 megahertz, then 2, 3, 4 megahertz, if there are signals at the output of a circuit at those frequencies, those are harmonics because they're integer multiples of the input. There are mixing products. If you have two frequencies in the input signal, then there's some indifference will also be present in the output. Sometimes you don't want this, for instance, in a linear amplifier, where you don't want to emit signals, spurious signals that make your signal wider in bandwidth or make you transmit energy outside the amateur bands completely. Sometimes you do want it. For instance, when you want to convert a radio signal to the intermediate frequency, in other words, take whatever frequency you're listening to and convert that signal to a fixed frequency, which could be higher or lower. There's what's called intermodulation distortion, which is if you are modulating, well, for instance, my voice contains, all of our voices contain energy at different frequencies. And when we modulate an AM or single sideband signal with that, um, we'll also in the modulator and in amplifier stages, we'll get what's called intermodulation distortion, where the sum and difference of the audio frequencies also modulates the carrier. So in other words, it adds energy at different frequencies to the radio signal, but they are close to the carrier frequency. Um, and what they do is they add distortion, and they can also make the signal somewhat wider. And then John talked earlier about limiting and clipping, where if you're looking at the waveform of an input signal, it's distorted. And um, we try to avoid that, except when we really want to do it. And if a circuit changes the waveform by uh, adding a minimum or a maximum to it beyond which the signal can't travel, um, that produces any or all of the effects that I mentioned before this. And last, I want to talk just a little bit about noise. Every active electronic circuit with tubes, transistors, diodes, and so forth adds noise to signals, and it's something that we generally try to avoid, and generally it's at a very low level. Now, noise is noise because it's generally random or repetitive, but not continuous, not a distinct part of a desired signal, is considered separate from distortion. It can be natural. The stars in the sky emit radio waves at certain frequencies, and when you get into the VHF and UHF bands, also the sun, uh, that is background noise. But also static discharge and distant lightning bolts can introduce noise. On the VHF bands and up, it's not usually very noticeable, but on the HF bands, you can definitely tell when there's especially on the lower HF bands, you can definitely tell, for instance, when there's a thunderstorm anywhere within a couple hundred miles. And there's also man-made noise, from generally from either arcs, electric arcs, for instance, in motors or the ignition of an engine, or it can be from digital signals that are rich in harmonics and are not well shielded. For instance, the circuits in your computer. The reason why every piece of consumer electronics you own has a label that says Part 15 is because the FCC, when personal computers first came out, realized that all these digital products and all these things that had electronics in them could interfere with radio reception and TV reception. So digital signals are worse, but they can be noise. They can be noise that we don't want to hear. Um, okay, so let me end this.
Yeah, don't forget static discharge too with the
Yeah,
power lines and uh,
static discharge is in there.
power
Is
lines and spark plug.
Yeah. Okay, so now let me go to the next thing here. Sorry, this is going to take a minute.
Well, I got it up, Wes.
Oh, you do? Okay. You want to do the next slide deck? Go ahead, John. It's all
Yeah,
yours.
did read the book. I just uh, didn't take care of my
Well, you or me, John. Take your
slide
pick.
deck. Here it is. Super heterodyne receivers
Okay.
invented in the 19 about 28 or 29, I think, by good old Armstrong. Most receiver used today by amateurs are super heterodyne. Another thing I wanted to say about the noise, when you get on HF, not on the FM, if anybody is so old as to remember AM radio, that's what it sounds like. All that extra noise in there that you used to get driving in your car. Received signals are incredibly weak, in the order of nano or picowatts. Received signals are first strengthened by an RF amplifier, then applied to an RF input of a mixer. Now the mixer is where we start with the heterodynes. The local oscillator is adjusted so the desired signal creates a mixing product at the intermediate frequency. A detector or demodulator stage follows the IF to recover the modulated information. Input amplifier gain, demodulator stage bandwidth, and input amplifier noise can all affect receiver sensitivity. Yeah, too much of that initial gain can make it noisy. So that's something us hams play around with a lot, is the initial gain of the receiver um, to get rid of the noise. Where did it go? There it is. There's a super heterodyne receiver. It converts signals to audio in two steps. The front end converts the frequency of the signal to the intermediate frequency.
Not for, only for letters, postage.
Yeah, that don't read quite right, does it? Because the first RF amp there converts the whole band you're on. So it can't limit it. It has to be a wide amplifier. It has to accept a wide range of signals. So then they run it to a mixer, and then the output of the mixer is a single frequency, and then the IF filters can be applied to a single frequency, amplify it, and then decode it here with the product detector. And finally, your AF amp. So that's pretty normal. A lot of this RF amp is a ham radio thing, or for weak signals. The old broadcast bands, a lot of time it didn't exist, the RF amp ahead of the mixer. Most of the gain, the receiver is provided a second mixer. The product detector converts the signal to audio frequencies. Well, yeah. All right, the front end converts the frequency of a signal to the intermediate frequency, where most of the gain of the receiver is provided. There can be multiple steps in here. This just shows one IF filter, one amplifier, but sometimes there's multiple ones. And the product detector converts the signal to audio. Um, before the super hat, you had to have an adjustment for each stage to retune the filter. Once amplified to a more stable, usable level, sideband and CW signals are demodulated by a product detector, a special type of mixer. If an AM signal is being received, the product detector or envelope detector recovers the modulated signal. That was one of the easiest of the early ones, was the AM. Simple electronically, I mean. Output of the detector is an audio signal amplified by an audio frequency amplifier and input to the speaker, headphones, or sound card. So it's modern. We got sound cards now. The RF amplifier and mixer are the receiver's front end. And that's where the noise can come in at. Processes weak signals at their original frequencies. The RF amplifier, the very first one. A pre-selector is often used to reject out-of-band signals. So almost all of the HF rigs, there's a series of tuning filters before the first amplifier, and they filter. So if you have a band that's 7 megahertz to 7.5 megahertz, so it's tuned for that band. So it'll have a pass band that wide from 7 megahertz to 7.5. And so it rejects those out of band signals, which can wipe out your signal if you're trying to listen to a real weak signal. A preamplifier is used if additional sensitivity is needed. That's the one we were talking about, the preamp. The simplest possible superhet consists of a mixer connected to an antenna and oscillator to act as the LO, local oscillator, and a detector that operates directly on the resulting IF signal. See figure. And a single frequency IF stages makes it much easier to create high quality filters and high gain amplifiers without them having to be tuned. Only the local oscillator needs to be tuned to the superhet receiver. Anyways, yeah, the old ones where you have multiple ones, your tuning adjustment would adjust a couple of variable capacitors. They'd all be connected to the same drive shaft. But now, thanks to superhet, you only need one. Recall the formula for intermodulation, mixing of signals, F1 plus or minus F2. For example, to convert an RF signal on 14.250 to an IF signal of 455, the local oscillator must be tuned to either 14.250 minus, so it's going to be tuned to either 13.795 or 14.705, either the one that's plus 455 or the one that's minus 4. I did it backwards, but either the plus or the minus, because you get both products once you mix them, the little mixers, and we mix them up a lot. Superhets have some weaknesses, like all radio designs. Because there are mixing products at both the sum and difference frequency, undesired signals can create their own mixing products at the IF. See the next slide for examples. Oh, there you go. Next slide, F1 plus F2. And whoops, another flaw is caused by the local oscillator and other oscillator circuits. Leakage of signals into the signal path can cause steady signals to appear. Oh, well, they call them birdies, but it'll be a tone just right there in the middle. You're trying to listen to an audio signal and there'll be a whistle in there. A birdie. Signal conversion with only one mixer converting. That's what we were looking at. The IF stages provide most of the gain and selectivity. Filtering is applied to each IF, allows filter bandwidth selection for desired signal. This gives the best received signal quality with the lowest unwanted noise and interference, maximizing your signal to noise ratio, which is what we're going after, a good signal to noise ratio. In a mixer with an RF input and an input frequency and a local oscillator, F1 and F2, remember there are mixing products at the sum and the difference. So here's some examples, and you got to believe it'll be on the test. With a LO of a local oscillator of 13.8, mixing product of 455 can be generated by a signal at 4255 or 13.345. And if you do the math, either way, it'll add up to 13.8, whether you add the 455 or subtract it. There you go. All the math in one spot. But the 455 is a pretty common. They have multiple IFs or intermediate frequencies, but 455 is probably the first one they ever used. Assuming that the intended signal at 14.255 is an image response. Well, did that make sense to anyone? I don't know. Why you worry about that? But that's
Go back to that image response there, John, if you would. I'm not sure what it,
yeah, I don't quite follow that one. The intended signal. Anyways, here we go. We'll do the math. Similar to AM sideband and CW superheads, the linear amplifier is replaced by a limiter. Oh, this is for FM. Yeah. Limiter amplify the received signal until all the amplitude noise is removed and only a square wave exists. So they just amplify the heck out of an FM signal until it looks like a square wave. The audio information is recovered by a discriminator or a quadrature detector that replaces the product detector. Yeah, I was used to the term discriminator, but a quadrature detector is also. Once an FM signal is converted to IF, high gain amplifiers called limiters change the signal to a square wave that only varies in the frequency, not amplitude. The discriminator converts the frequency to an audio. And so there's the signal diagram. Again, an RF amp going to a mixer, going to an IF filter. The limiter's what's different, and it just turns the sine waves into square waves by over amplifying them, and then you can convert it to an audio sound wave. And so we're going to move on to DSP, by golly. The new thing. What's it doing there? The general term for converting signals from analog to digital is called digital signal processing. Figure below. Systems use an analog to digital converter to change the signal to digital data. The special type of microprocessor that performs the mathematical operations on the data is accomplished filtering, noise reduction, or other function. To accomplish. A digital to analog converter changes the process data back from analog to output as audio. It takes the audio out. Having trouble seeing this. My screen is messed up here. So that's the diagram. Yeah. They took a while to get the ADCs running fast enough at those speeds up in the megahertz. Two advantages over the analog circuitry: performance and flexibility. DSP offers selectable pre-programmed filters and allows the operator to adjust the filter bandwidth and shape, and even to define new filters. Expensive functions in analog circuits can be implemented in DSP as a program without additional hardware. So once you get it converted, you can work on it with the do the math in a program. When looking for weak signals, set RF gain to maximum for highest receiver sensitivity. Yeah, this is a difference with HF. These type of adjustments you don't usually see in FM and that. Lower the RF gain volume to reduce the background noise. Because why amplify noise? You know, so you turn down your RF gain, the radio frequency gain, not the audio frequency gain, to reduce the background noise. It just lowers that noise below the threshold of the noise, and you don't hear them anymore. Automatic gain control circuits vary gain of the RF and IF amplifiers, so output volume stays constant for both weak and strong signals. Well, the AGC is kind of a sneaker. I mean, it's really important, and it's actually used in a lot of different type amplifiers, but with HF amplifiers, they give you a control for it, so you can adjust the amount of gain. It's a kind of an outer loop in the feedback of the gain of your rig, and you can adjust how fast that loop is. This voltage is read by the S meter, measuring signal strength. Yeah, that's kind of magic to me, but it works. The AGC circuit, as it moves, as the amount of AGC, the control voltage changes, that is the analogous to your S meter. So the AGC level is actually your S meter level. And as you turn down your gain, you'll see the your S meter go down or up, depending on which way you're moving it there.
I understand
Okay, yeah.
yeah, I understand the AGC. What I didn't or don't understand is what has the speed got to do with it?
Oh, well, if you have like if it's well, for one thing, there's background noise on HF, and
Right.
that's one case where that background noise can be going up and down, and the part you're hearing, the audio will be going up and down. So you can go to a slower AGC and avoid that constant change. A lot of times you can turn your AGC down and eliminate some of the noise.
Okay, so what do they do? Just kind of charge up a cap to put a delay
yeah,
in
it's
there?
actually a feedback loop.
Yeah.
Going from the
Okay.
output of the amplifier, I mean the audio output, and it feeds back to all the gains of all the amplifiers in that chain we were looking at before. So it's the gain of the amplifiers, especially in the IF section. It controls that gain. So if you're listening to a strong signal, you can turn down your gain and it'll reduce the interference from the low strength signals. But
Yeah, I was just trying to figure out how the speed. Yeah,
yeah,
I understand what the AGC does. I just didn't understand what the speed factor was.
yeah, and the reason is that the signal strength is going up and down on those frequencies. It can with with your high frequency signals bouncing through the ionosphere, it can go up and down in strength. And sometimes you want the AGC to follow it, so you'll get the gain to go up as the signal gets weak. Other times it's like interference that'll, for one thing, other signals on the band, if they're real strong, they can make your AGC activate and it'll turn down your gain, even though that's not the signal you're trying to listen to, if you know what I mean. If there's two signals within your bandpass, they both can affect your AGC.
Gotcha.
Yeah, I typically keep mine pretty slow, but sometimes you'll get into a band where it's just going up and down and up and down, and you just go to the slower one. Most rigs have some sort of an adjustment for that. So here's one of the mysteries. S meters are calibrated in S units. 1 S unit equals 6 dB, fourfold, 4 times change in signal strength. So, but 1 S unit equals 6 dB. That is probably on your test. That fourfold, does anyone know what he's trying to say there? Fourfold equals
Yeah,
four.
I think 3 dB doubles everything. Is that correct?
Okay, yeah. So that would be 4 times would be 6 dB. Okay,
Yeah.
thank you.
I didn't follow that. I'm sorry. So if it increases it 3 times and it's fourfold, how is it 6?
Well, 3 dB is twice. A 3 dB gain would be 2 times gain, and so 6 dB would be two
I
times 2 and 4.
Okay.
And I think we have a whole section on dB, and I think that's
Okay. I
we're
got
a
it.
little out of order here. Because eventually you guys will have to learn how to calculate dB with your old slide rule or whatever.
Yeah, I got it.
S9 is kind of the desired. That's a good strength signal. It's located midway of the display, larger values to the right, 20, 40, 60 mean 20 dB over S9. As it says there, these correspond to dB over S9. So 20, 40, and 60 dB over S9. And a reading of S9 plus 20 dB is a signal 20 times stronger than an S9 signal, or 100 times stronger, because 20 dB is 100 times. Like I say, we'll go through that slow motion of dB, which is 10 times the log of the base 10 of the ratio. Oh, we done with that one? Reading an S9. Well, now that's we talk that language a lot, S9 plus 10 dB or whatever, and we don't go through the calculation in our head, but you'll have to for the test. If the received signal is distorted, spurious signals will appear just as if transmitting station were emitting them. Yes, sirree, because there's no channelization here. All the signals on HF, well, other than 60 meters, they can be wherever the operator sets them, so that you can kind of drift in and out. And since skip varies depending on where in the country you're hearing from, it can really get interesting. Most common form of receiver nonlinearity is overload, also called front-end overload or gain compression. Well, okay. Front-end overload, it kind of blanks out on you there. Solution to overload is to filter out the offending signal or reduce the receiver gain. Proper use of attenuator and RF gain controls can dramatically reduce the received noise distortion caused by strong signals. So as a result, when I'm on 80 or 160, which are noisy bands, I usually kick in that 20 or 40 dB attenuator. There's one right in the front of your receiver. Rejecting interference and noise. IF filters narrow the receiver's passband, removes unwanted signals. Well, the ones that are outside the passband are gone. I hope it's not what you wanted to hear. Notch filters remove signals in a very narrow band of frequencies, such as signal tone from an interfering carrier. I think we went through this on a previous section with this notch filter thing. Passband or IF shift adjusts receiver's passband or above or below the displayed carrier frequency. Avoids interference from adjacent frequencies. In other words, on on these HF, so you can adjust the frequency wherever you want within your band allocation. And so a guy can be kind of close to you on one side or the other, or he can be wider than he's supposed to be. And so you'll hear this funny noise of him interfering on the side. You don't quite copy everything, but by turning down by adjusting the passband or going to a more narrow filter, you can filter that out until you can't hardly understand because you start by just taking the very low and the very high frequencies down. You just cut them out. And a lot of times, as long as you get the middle part of the audio, you can usually copy them, depending on the conditions. Reverse sideband control allows switching between receiving CW signals above the carrier frequency or below it. Avoids interference by placing the signals on the other side of the carrier where filtering rejects them. Yeah. They talk about this a lot, and it will be on your test. And I don't think I've ever used it, but it's because it's just a CW thing. So you can switch it, and sometimes that'll clean up the signal from a adjoining adjoining conversation. These CW signals are incredibly narrow, anyways. Usually 50 hertz or 100 hertz. So they got pretty good filters. Noise blankers sense short, sharp pulses in the IF signals and reduce the gain of the IF and audio amplifiers during the pulse, called blanking. Adjustable noise blankers can be set to blank the receiver at different noise levels. Yeah. The first practical use for those, I always remember, was ignition noise. If you have an HF rig in your car, especially some cars, you can hear I can hear noisy cars drive by on the street sometime. Most modern cars don't have that problem, but because they put suppressors on each spark plug wire. But sometimes you'll hear them, noisy lawnmowers or something. So noise blankers can be set to get rid of that. I've also used it just if you hear like a clicking noise or some real quick little interference. Sometimes it'll take those out too. Noise reduction is performed by the DSP. This has been really something. This didn't really come along until like the 1990s, I don't think. And boy, it really helps. Removes hiss and noise from the audio that is not part of the desired speech data or CW. Increasing the noise reduction level may cause some of the desired signal to be removed, causing distortion. Use the least noise reduction required to minimize this. So I do nowadays the DSP level can be adjusted pretty nicely. The first one I bought, it was either on or off, but now you can adjust the amount of DSP suppression you want. So I usually leave a little bit of it in there. What is the purpose of a notch filter found? Oh, I did it again. Practice questions. What is the purpose of the notch filter found on many HF transceivers? The notch filter, to restrict transmitter voice bandwidth, to reduce interference from carriers in the receiver passband, to eliminate receiver interference from impulse noise sources, to remove interfering splatter generated by signals on adjacent frequencies. Well, to restrict the transmitter voice bandwidth, to reduce the interference from carriers in the receive band passband, to eliminate receiver interference from impulse noise sources. Boy, they're hitting them all. To remove they're covering most of the receiver filtering you can use. So now this one is the notch, which is that very narrow filter, which would be good for eliminating what? it would eliminate a single tone. That's what we use them for primarily, which is caused by carriers on other transmitters.
I'll take a shot at it. How about B?
Yeah, it's
Yeah, that's kind of
B.
what I think it is too.
Yeah,
Yeah.
it is.
And you kind of gave it away a little bit when you talked about that. Very
I
narrow.
was slowly trying to do that.
Carrier is very narrow.
Yes, there you go. What is one advantage of selecting the opposite or reverse sideband when receiving CW? Interference from impulse noise will be eliminated. More stations can be accommodated within a given signal passband. It may be possible to reduce or eliminate interference from other signals. Accidental out-of-band operation can be prevented. Ooh, well, that's kind of illegal.
I
D.
think it's C.
It's C. I think you're right. It is. Yay. C it is. Interference from other signals. How does a noise blanker work? That's one that we almost guessed. Temporarily increase receive bandwidth by redirecting noise pulses into a filter capacitor, by reducing receiver gain during a noise pulse by clipping noise peaks.
It's C.
Oh, I'm going to get off that mouse. I got a mouse that double clicks on me a lot. All right, it was C. Reduces the gain during a noise pulse. I've used them for years. It wasn't until I got to teach in this class that I knew how they worked. What happens as a receiver's noise reduction control level is increased? Receiver signals may become distorted. Received frequency may become unstable. CW signals may be severely attenuated. Received frequency may shift several hertz. So they're telling you what's wrong with this noise.
It's A. It's probably A.
A. I think that's the only one that made sense to me. A it is. Yep. They don't tell you what they want you, what you use it for. What is the purpose of using a receiver attenuator? Receive attenuator. To prevent receiver overload from strong incoming signals, to reduce the transmitter power when driving a linear amplifier, to reduce power consumption when operating from batteries, to reduce excessive audio level on strong signals. Now this attenuator is way up at the front of the chain, way up there at before the first signal amplifier in the receiver chain. It's the very first thing you hit. You just cut that signal down right away.
And
Okay.
and D is at the other end, the last thing that you do. So
Yeah,
it's kind of telling you what it is. You can eliminate D and you're still with A.
yeah, it is. Prevent overload, because if you have a real strong signal, it could overdrive those sensitive amplifiers in the beginning of your receiver chain. And A it is. What does the S meter measure? Carrier suppression, impedance, receive signal strength, transmitter power output. And yeah, I want to give you a hint here. That S, the S meter, the S stands for
Signal strength.
huh?
Signal strength.
Yes, it is. The S, the signal strength, C, S. Wow, that's English too. Whoop, I gotta quit using the mouse. How does a signal that reads 20 dB over S9 compared to one that reads S9 on a receiver, assuming a properly calibrated S meter, which we'll let that one slide. So 20 dB is 10 times less powerful, reads 20 over S9, 20 times less powerful, 20 times more powerful, 100 times more powerful. So it's the relative strength of your received signal. And 20 dB, like I said, we'll get to dB calculations, but divide 20 by 10.
Since I had asked that question, and I think I may remember, but I'm a little over 30, I would say D delta.
How many?
D delta.
Oh, D delta. D delta it is. Yes.
How about that? I remembered.
Yeah. So that dB is a log 10. So and it's 10 times that. So you divide 20 by 10, and then uh anyways, it is 100. Two 10 10 squared is 100. So dB of 2. Well, anyways, I'll quit mumbling until we get to that unit. How much change in signal strength is typically represented by 1 S unit? And this is one you got to memorize, just plain old. I mean,
Okay. I think I'm going to go back to that same thing, and now I'm going to say I think my memory is A alpha 6 dB.
yeah, I didn't remember who, but one of you guys came up with that 6 right away, and that is right. 6 dB, 1 S unit, or 4 times. We went through that, didn't we? 4 times.
Yes, sir. it Did.
How much must the power output of a transmitter be raised to change the S meter reading on a distant receiver from S8 to S9, which is 1 S unit, right? So 1 S unit is
B Baker.
B Baker. I think it's Charlie.
Yeah.
Yeah, it is, Charlie. I think
Yeah.
we covered that on the last question fundamentally.
Yeah, they kind of hinted at it, didn't they?
4 times. Yeah, you're right.
Represented as 4 times. Yeah.
So 60.
Okay. 4 times. 3 dB is 2 times.
Yep.
Okay. How is a product detector used? Used to test gear to detect spurious mixing products, used in transmitter to perform frequency multiplication, used in FM receiver to filter out unwanted sidebands, used in single sideband receiver to extract the modulated signal. You couldn't tell by my voice, huh? Oh, well. So a product detector. So that's the one that converts the carrier with all the information on it to an audio signal. That's what that stage does.
Hmm.
It extracts the
I
modulator.
don't like any of them. But
Well,
Take a guess on C Charlie.
yeah, it's a dog.
Oh my, it is a dog, isn't it?
Yeah, they use 2 different words. The product detector is for an AM or sideband signal, and I forget what they call the other one. We'll probably get to it here. I'll go back and look it up, but it's not the product detector, it's the Which of the following is an advantage of a digital signal processor filter compared to an analog filter? A wide range of filter bandwidths and shapes can be created. Fewer digital components are required. Mixing products are generally reduced. The DSP filter is much more effective at VHF frequencies. Well, I'll tell you, they made up 3 of those answers. They're not true.
It's alpha, I think.
Yeah, it is. It's just a universal. You don't need to change components. You just change your program to get to the different bandwidths and shapes. Oh, I can hear the words for it now. All those filtering techniques. Oh, the math it's just wonderful. Which parameter affects receiver sensitivity? What parameter affects receiver sensitivity? Input amplifier gain, demodulation stage bandwidth, input amplifier noise figure. All of these choices are correct. Well, pooey.
Yeah,
See, I
I
don't
think
like
it's alpha.
that Charlie input amplifier noise figure. We haven't covered noise figure at all. And it's a very complicated concept as far as I'm concerned. I think it's D myself. Yes, it is. Yeah,
Yeah, okay.
everything. And but like I said, noise figure is the one that gives it away. It's anyways. We'll get there, I think. Which mixer input is varied or tuned to convert signals of different frequencies to an intermediate frequency? Which mixer input is varied or tuned to convert signals of different frequencies? Image frequency, local oscillator, RF input, beat frequency oscillator. Beat. Oh,
I heard B.
B.
Yeah, bravo.
Okay. Ah, you're right. I saw it flip by there. It kind of bothers me because the BFO is an old word for almost the same thing.
Yeah, that was used back in the old days for extracting CW or single sideband, was it?
Yeah, yeah, you're right. That's your BFO. You mix it with the incoming audio and it generates the da da da, the BFO. What is the term for interference from a signal at twice the IF frequency from the desired signal? What is the term for interference from a signal at twice the IF frequency from the desired signal? Quadrature response, image response, mixer interference, intermediate interference. Wow. Hmm.
Well,
Mixer.
Response, mixer interference, intermediate interference.
Maybe it could
Quadrature?
probably end up being B because image has got the plus and minus.
Yeah.
I think it's A.
Hey,
I think I'll go with Carrie. I would say A.
Because you got the
it's B.
cosines, the sines in there, and the Fourier stuff.
Image response.
Yeah, that's
Image?
because you generate the your IF frequency, the plus and minus of your IF,
Yeah.
sum and difference.
So you got one that's twice what you wanted there that you'd have to filter out. Um, image response. Okay. One for the old gray matter. What? Why is it good to match receiver bandwidth to the bandwidth of the operating mode? Receiver bandwidth, okay. It is required by FCC rules. It minimizes power consumption in the receiver. It improves impedance matching of the antenna. It results in the best signal to noise ratio. Well, if you understood all those, for one thing, FCC rules, they don't care anything about your receive, and this is receive bandwidth, so can't be that one. And minimizes power consumption in the receiver. Yeah. It
I
improves
think
the
it's delta.
impedance matching. Nah. Yeah,
D.
it's got to be a delta, don't it? It is. And we're done. All right. I wonder why this is the one.
Okay, let's take a break here.
Yeah, bye. It's after 8, isn't it?
Yeah,
Yeah,
let's take a 10-minute break until 8:25. And John, can you stop sharing your screen for a second?
Oh yeah, I think so. How do you do that? Right there, the red one.
Yeah,
There we
there we
go.
go. We have a new person or two. We have Tony KE8LXY. Is that the correct call sign for you?
Yeah,
yes,
there.
sir. That's me.
Hi.
How you doing?
Say hello a little bit. Show us
Yeah.
who you are.
Well, yeah, I know a couple of the guys on there, John and Larry. So I've worked with them, a retired television broadcast engineer. But I do have a question for you, Mr. Teagarden. Um, I was trying to follow what you were talking about in the book, in the manual here. Can I find more of what you were talking about in the book?
Where?
In the
So we're in
Jer-
section 5.
in section 5. Okay.
Yeah, we're trying to finish it. And yeah, so the only thing left is mobile installations in section 5. So yeah, we've been in the first part of section 5 for a couple of weeks now.
Okay. Because
Wait till we get to
I was
section.
just trying to keep up with you and follow along in the book.
Okay, yeah, these slides are pretty much copied from the book. So
Okay.
Okay. Tony, after tonight, what I'd like to ask you to do is, as I said in the email that I hope the Colonel forwarded to you, send me an email and I will send you some of the handout material from the last few weeks. And then also you should be sending an email to Bob N8REL, who is our registrar, so we can make you official if you decide to stick around after you see our performance tonight.
Well, I've been ordered. I have to do that. Yes. So no problem. I'll drop an email after class.
Super. Okay. All right. And I want to say good evening to Larry, who's sitting in tonight, and to Ken K8SJW. Good evening. Okay. So
Good evening.
break till about 25 past the hour, I think. And we'll let it go a couple minutes beyond that.
okay, I hope so. Share. HF installation. So after you get your ticket, you can get your upgrade, I guess. Then you can do one of these. I'm trying to set up an HF mobile, and it's harder than it looks. That's all I can say. HF operating with longer wavelengths and higher field strengths makes grounding and interference control much more important. It sure does. I just had a grounding problem. The general exam focuses on 3 related areas: mobile installations, RF grounding, and RF interference. So there we go. Mobile radios can output 100-watt required. Mobile radios that can output 100 watts require solid power connections capable of supplying 20 amp or more. Yep. And cigarette lighter out just don't work. Not at 20 amp, even though they might be rated for it, but they droop. Solid state radios perform unpredictably with input voltage when input voltage drops below the specified minimum power supply voltage. Best power connection is directly to the battery, heavy gauge wire with both leads fused. And yeah, I don't think the automotive people like it much, but it really is. It's pretty legal and all. I had a car in at the shop and they saw my wiring connected to the battery and they disconnected it, and I got it home and connected it up again. And I even had fuses on it, so I don't know what the problem was, but it wasn't factory. Do not use cigarette lighter or aux socket, usually rated at only a few amps, insufficient to supply a 100-watt radio. If you have an older vehicle, something from the 1980s, for example, it may have old-fashioned cigarette lighter socket related with enough amps to power your radio, but confirm with both owner manuals before you try it. And if you guys have used those plugs that you plug into your cigarette lighter, then it's got 2 wires that you can run over to your radio. I just melded one of those. It was for one of those solid state coolers, and I'd run it for years on this. And the last time I had it on, the little plug thing just got really soft and hot, and the fuse melted, or the solder melted in the fuse. So they're not really good for that. Every machine operated wrongly enough becomes a smoke machine, well, or a melt machine. Antenna connections. A limitation of mobile installation is that electrically short, smaller in terms of wavelength, antennas are less efficient than full-sized ones, particularly true on lower frequency bands like the HF. Tips to improve antenna performance. Use the most effective antenna you can. Make sure your ground connections to the vehicle are solid. Mount antenna wire where it is clear of metal surfaces. But the ground connections I found is really important, especially on like 40 meters, 80 meters, because you're using the metal of your car as part of the antenna. So being grounding is pretty important to complete your antenna circuit there. Mobile interference. Different interference sources than home. For example, ignition noise, spark plugs firing, not applied to diesel engines, of course. Of course, diesels are noisy anyway. I mean, audio noise. Alternator whine, which is usually, nowadays, if you have alternator whine, there's something wrong with your alternator, I would assume, but it used to really be there. We say they hummed, but it's just because they didn't know the song, I don't think. Vehicle accessories can generate noise. Onboard control computers can generate noise. You can also wipe them out. Electric motors in fuel pumps, windows, and battery charger systems. And boy, if you have an HF rig on at the time, I remember you could hear the the window motor when you went up and down. You could hear the noise. Winch motors. Okay, grounding and bonding. Now this is a little more down to earth. AC grounding prevents hazardous voltages from appearing on a equipment chassis, creating a shock hazard. To manage RF, bond equipment enclosures together. Bonding means to connect 2 points together to minimize voltage between them. Well, okay. During digital operation, unwanted RF currents can cause distortion, erratic operation of computer interfaces, activate transmitter improperly, garbled digital protocols. Yeah, I have one band in particular I have this problem on. So here's what you're supposed to do to solve the problem. Mostly it's have a single point of bonding, have all the pieces of equipment in your shack that have RF in them, have them bonded to a common point. This is an example of typical RF bonding bus at the operating position, helps keep all the equipment at the same RF voltage. And sure enough, a nice copper pipe is an easy way to do that. Bonding basics. Connect all metal equipment enclosures directly together to a common RF bonding bus. I think they're going to get to why you want to do that. Keep connections strapped and wires short. Use short, heavy conductor, number 12 or 14, or a strap, which they mean that braided ground straps. If strong RF is present, use a piece of wide flashing or screen under the equipment connected to the bonding bus. Okay. If ground connection is resonant at an odd number of quarter wavelengths, it will generate high impedance, enables RF voltages on enclosures and cables. And I have that problem because I have my shack in the attic, so I've got to have a pretty long ground wire down one floor. So that gives you, and I think that's why my 10 meters, it really gets noisy. Ground loops are created by a continuous current path around a series of equipment connections. Oh, ground loops. Loops act as a single turn inductor, picks up voltage from magnetic fields, from transformers, AC wiring, results in a hum in the transmitted signals or that interferes with control or data signals. Yeah, I get that's what I get on 10 meters because my ground's too far. I got an artificial ground for a while, but they have to be tuned with every frequency, so that isn't a good fix, I don't think. Ground loops can be avoided by connecting all ground conductors to the RF bonding bus. Well, shoot. The point is, it's a star. You have all the grounds going to that one cable back there they were talking about. Here, you don't want a ground loop which would run the well, um, anyways, by having each piece of equipment going back to one ground. In other words, if the two pieces of equipment are grounded together, which a lot of times, like your computer and your transceiver, you got a cable going from the computer to the transceiver. So there's the potential for a loop right away. And just about all these things, like the keyer will have a wire going to the computer. It's just really easy to get a ground loop in it. So a good star ground is best. RFI causes and solutions. Fundamental overload. Radio TV receivers unable to reject strong signals causes distortion or inability to receive the desired signal. Prevent signal by using filters in signal path. A common solution used to be and it'll just happen on one band. I forget which, or we use antenna TV, and it would only interfere on one station. I can't remember which one when I was on a particular band. Common mode direct pickup from electric equipment with internal electronics picked up on the outside of cable shields and conductors of unshielded connections. Block current with RF chokes. These RF chokes, they're just put them everywhere. Harmonic spurious emissions from amateur radio may be received by a TV or radio. There's no first harmonics. It's called the fundamental frequency. Well, use low pass filter at the transmitter, which, yeah, I just about always have I think it's 30 megahertz filter, low pass filter for the output of my HF rig, especially with an amplifier. You gotta filter them out as best you can. Intermodulation, poor contacts between conductors picking up RF signals can create nonlinear connections that acts as a mixer and mixing products from the signals. Find and repair poor contact or block. The RF signals look for odd order harmonics closest to the original frequencies. The thing about harmonics they're slipping in here is the harmonics are always the multiple of the fundamental. So the harmonic frequency is always above the frequency you're broadcasting at. So it's twice, 3 times, 4 times. Arcing, a spark or sustained arc creates radio cracking or buzz over wide frequency range. It may require a power company to make repairs, filter specific equipment. Yeah, that's kind of a perennial problem is the insulator on the very high voltages. Even in your neighborhood, you've probably got 13 kilovolt up at the top wire, or at least 4 or 5. So they get wet. The other day I was operating in it. We had a fine mist, and all of a sudden I was getting all kinds of buzzy noises. Common RFI. RFI is quite varied. Some more common types are wrong one. CW, FM, or data. interference consists of on-off buzzes, humming, clicks, or thumps when the interfering signal is transmitted. Yeah, CW is kind of a blanking sound you just hear with each pulse of your CW. The AM in that, it interferes. Usually you can hear it in the audio. AM phone equipment experience overload or direct detection will often emit a replica of the speaker's voice. Yeah, and that's the beauty of sideband is it sounds like a duck, so hide your voice a little bit. SS sideband voice similar to AM phone, but voice will be distorted or garbled. The Donald Duck sound, you know. If you've never heard sideband, it's always exciting when you first hear it. Filters are effective and easily to install, suppressing RFI. Sometimes a simple cap will work on your coax going into the TV, for example, or on your audio signals too. Block RF by placing an impedance in its path. Form conductor carrying RF current into an RF choke by winding it around or through a ferrite core. Yep, I didn't bring examples, but they're pretty common. They even make ferrites that are they open up so you can wind around them and then you close them up around it. Ferrite beads placed on cables to prevent RF common mode from flowing on the outside of cables and shields, which is where they always flow, is on the outside. And the most common place you really have the problem is the signals going into your computer, the cables going from the RF from your rig to the computer. I see more of those. You'll have like sound cards or control cables, and sure enough, you'll get some noise that'll wipe you out. You know, all of a sudden your Wi-Fi quits working or something. Interference to audio equipment and sensor connections can be eliminated by using small 100 picofarad or 1 nanofarad bypass capacitors across balanced connections, because capacitors pass high frequencies. Which of the following might be helpful in reducing RF interference to audio frequency devices? A bypass inductor, a bypass capacitor, forward bias diode, reverse bias diode. Well, there's only one thing we did mention inductors, didn't we? And capacitors. But we never mentioned diodes, so we can throw those away. So we only talked about both inductors and capacitors, but okay, the simplest is a capacitor. Let's see if they like the capacitor. Yes, they do like the capacitor. Inductors, you typically you don't put them in circuit. You just wrap the cable around the inductor, around the ferrite core. Which of the following could be the cause of interference covering a wide range of frequencies? Not using a balun or line insulator to feed balanced antennas, lack of rectification of the transmitter signal in power conductors, arcing at poor electrical connection, using a balun to feed an unbalanced antenna.
Arcing. If that wouldn't do it, what would?
Yeah, oops. Just can't get it right. You're right. That was the only one that fit all of them. You're right. Arcing. And the beauty of like a lightning strike type arcing, it's on all the frequencies. You can look any band, any frequency, and you'll see that the arc it's all frequencies are contained in those arcs. What sound is heard from an audio device experiencing RF interference from a single sideband phone transmitter?
Distorted speech?
on, off, humming, or clicking.
No. Distorted
Distorted
speech.
speech, clearly audible speech. A steady hum whenever the transmitter is on the air. Huh. Did anyone say C? That'll be my guess.
Yeah, I think it's C.
Yeah, it's C. The on-off humming and clicking would be if it was a CW. They don't tell you what kind of well, it says an audio device. Yeah, no. But yeah, if someone's transmitting CW, it's more of a clicking sound. What sound is heard from an audio device experiencing RF interference from a CW transmitter? As I said,
Well, it's not speech.
severely distorted audio CW signal at a nearly pure audio frequency. On and off humming or clicking. Any guesses?
On and off humming and clicking.
Yay, A it is. A. What is a possible cause of high voltages that produce RF burns? Flat braid rather than round wire has been used for the ground wire. Insulated wire has been used for the ground wire. The ground rod is resonant. The ground wire has a high impedance on that frequency.
Yep, it's delta.
Delta?
Yep.
It sounded right, didn't it? Yep, it is. Ground wire has high, they didn't say whether it was too long, too short, bad ground. Well, if you've ever done industrial grounding where they actually weld the ground wire to the stake. Heating of, okay, what is a possible effect of a resonant ground connection? Overheating of ground straps, corrosion of the ground rod, high RF voltages on enclosures of station equipment, a ground loop.
Probably C.
I think so. I don't know how that ground loop kind of threw me off because it is C. Which of the following would reduce RF interference caused by common mode current on an audio cable? Place a ferrite choke on the cable. Connect the center conductor to the shield of all cables to short circuit the RFI signal. Ground the center conductor of the audio cable, causing interference. Add an additional insulating jacket to the cable. Well, it looks like only one of those makes sense to me. Insulating jacket has nothing to do with it. Ground the center conductor of an audio cable. Well, then it wouldn't work anymore, the audio cable.
Right.
Yeah, connect the center conductor of the shield to all cables to short circuit the RFI signal. But it's going to short circuit everything. So A's the,
Right. It's
Looks
gotta
like
be
A.
A.
yeah, A it is. How can the effects of ground loops be minimized? Connect all ground conductors in series. No. Connect the AC neutral conductor to the ground wire. Boy, they hate that. Avoid
Oh,
using,
God, that's illegal. Bootleg.
yeah, back in the crystal radios, we used to do that. Avoid using lock washers and star washers when making ground connections. Avoid? Well, anyways, bond equipment enclosures together.
D.
Dog it is. What could be a symptom caused by a ground loop in your station's audio connections? You receive reports of a hum on your station's transmitted signal. The SWR reading for one or more antennas is suddenly very high. An item of station equipment starts to draw excessive amounts of current. You receive reports of harmonic interference from your station. Wow. So you got a hum on your signal. The SWR goes crazy. An item of station equipment starts to draw excessive amounts of current. you receive reports of harmonic interference from your station, which would mean they hear you on another frequency, I assume, the harmonic interference.
I'd probably say A again.
Yeah, I think I would. Let's see what it says. Hey, it is. Yay. What technique helps to minimize RF hotspots in an amateur station? Building all equipment in metal enclosures, using surge suppression on power outlets, bonding all equipment enclosures together, placing low pass filters on all feed lines.
C.
B,
C.
dog,
Bonding.
bonding, bonding.
Yeah,
Charlie,
that's it.
yay. Just like in the picture, huh?
What are you doing? Get out of there. Get out of there. You crazy kid.
Why must all metal enclosures of station equipment be grounded? It prevents blow and fuse in the event of an internal short. It prevents signal overload. It ensures that the neutral wire is grounded. It ensures that high hazardous voltages cannot appear on the chassis. So,
Gotta be D.
yeah, it's gotta be. I read it with feeling. Which of the following direct fused power connections would be best for a 100-watt HF mobile installation? To the battery, to the battery using heavyweight gauge wire, to the alternator or generator using heavy gauge wire.
B is ridiculous.
Yeah,
C is ridiculous.
yeah,
D is ridiculous.
I think A is the only one, huh?
Yeah, those are pretty silly.
Yeah, there it is. Why should DC power for a 100-watt transceiver not be supplied by a vehicle's auxiliary power socket? The socket's not wired for it. The socket's wiring may be inadequate for the current drawn by the transceiver. The DC polarity of the socket can be reversed. That was Plymouth for that way. Drawing more than 50 watts from this socket could cause the
Oh,
engine.
that's ridiculous.
Yeah,
It's B.
Baker.
Yeah.
Yeah, that was the only one that really made sense. Which of the following most limits the HF mobile installation? Picket fencing, wire gauge of the DC power line to the transceiver, efficiency of the electrical short antenna. This is limiting. FCC rules limit mobile output power to 70 on the 75-meter band.
The junky antenna.
Yeah, it's got to be an electrically short antenna. Yep, it is. So you just put more power to it. Yeah. Which of the following may cause receive interference in a radio installed in the vehicle? The battery charging system, the fuel delivery system, the control computers. All of these choices are correct.
D delta.
Yeah. They don't say this in any of this, but this is just an aside. Those control computers, yeah, I think you can blow them up too with your RF, because I had one die on me. They didn't point the finger at my RF, but I
Is
think
that the control computer of the rig or of your car?
of your car.
Yeah, that'd be expensive.
Yeah, I blew out my the security one that your fob works with. How does a Faraday beater or core reduce common mode RF current on the shield of a coaxial cable? By creating an impedance in the current's path, by converting common mode current to a differential mode, by creating an out-of-phase current to cancel the common mode current. Ferrites expel magnetic fields. Well,
A.
yeah, I was going to say that's my EE background. It's got to be impedance. Yes, it is. I mean, that's how they work, I guess. They create a high impedance in the path. Which intermodulation products are closest to the original signal frequencies? Which Second harmonics,
Odd order,
order, odd order.
odd order.
Oh, odd order, it says.
Yep.
Let's see, we'll see that. I don't remember that in the three. Anyways, okay.
They explain that in the book. It didn't make sense when the first time I looked at it. Then I actually went back and read it, then it made sense.
Yeah, when they said that there's no first order harmonic. I think they said that there's all a so
Yeah, it's a
odd order
fundamental.
are closest to the original signal frequency. Or yeah, okay. The first harmonic. What process combines two signals in a nonlinear circuit or connection to produce unwanted spurious output? Intermodulation, heterodyning, detection, roll-off. What process combines two signals in a nonlinear circuit or connection to produce unwanted?
It's not B.
No, I think it's A.
It is. It is A, according to my little cheat sheet here. Intermodulation. Well, when two signals combine, that's what you get. Well, heterodyning looked pretty good too, but we'll take intermod. Which of the following is an odd order intermodulation product of the frequencies F1 and F2? Odd order. Oh my, 5F1 minus 3F2, 3F1 minus F2, 2F1 minus F2. All these are correct. So an odd order harmonic intermodulation product. Odd order. So 5 minus 3 is 2. 3 minus 1 is 2.
It's gotta be C.
Yeah, that would be Charlie, huh?
Yeah.
2 minus 1 is 1. And it is. How to calculate mixing products. The odd order intermodulation refers to a harmonic. Since odd order harmonics are closest to the original. That was the one there. But it's which of the following is an odd order? Okay. You can see the second harmonic is represented by the harmonic. So the two intermodulation thing. Okay. And the answer is oh, we almost got to the that is the end. All right. Take her away, Wes. That was kind of trick at the end, I thought.
Your timing is impeccable.
Okay, there we go. So I am going to spend about 15 minutes here so we can all go home at 9:15 and just get started a little bit on digital modes. And I want to point out that you carry a digital communication system in your pocket or purse, probably every one of us tonight, because the well, all cell phone systems these days uh, use digital encoding. So you're not transmitting an analog signal at all. So anyway, let's see here. Bear with me a moment and I will start the slideshow.
Oops. Huh.
Okay, hang on.
Okay, yeah, they got your co-host, so that should work.
Oh, here we go. PowerPoint slideshow. There we go. All right, can everybody see the title slide?
We got it.
Yep.
Okay. So I'm going to talk about some stuff first that's not really in the manual, but may help make things clear to you. We're going to cover chapter 6 here, digital modes. And uh, just to summarize, a digital mode is text, data, voice, or images transmitted as bits. Um, in other words, if it's voice or images, which are analog, it gets encoded into digital bits somehow. And of course, text and data start out as digital bits. Some digital modes are commercial but are used by amateurs. Some are only used by radio amateurs. Some modes are very historic, like radio teletype, and some are very new. Um, and the FCC regulates digital modes. Um, Boy, I got a typo in there somewhere. By type, data rate, and bandwidth, depending on what band you're on. So when you talk about digital modes, there are a lot of them, and I will be quite honest here. All the acronyms you're going to run into, both for the names of modes and for things that describe them, are real alphabet soup, and you're going to have to do a lot of memorization for this. And I apologize, but there's really not much of any way around it. Okay, so the most popular digital modes, the most popular by far is FT8, and there's a slightly faster version for contest called FT4. That came about, I would say, it first got popular during the pandemic, so it's only about 5 years old. There's radio teletype, which uh, is pretty much what the name says, and radio ham started doing that in the 1950s. So you can see there's quite a range of ages for these different modes. There's PSK 31 and PSK 63, which are conversational packet radio modes, which operate a lot like sending messages over the internet. There's Whisper, which is designed to tell how far your signal gets, how far it propagates in this country or internationally. There's slow scan television, which it transmits images in anywhere from about 15 seconds to 2 minutes. And then there are various digital voice schemes, D-Star, DMR, System Fusion, I think P25 is one of them. Those are all pretty much confined to VHF and up. There's something called free DV, which can operate at narrow enough bandwidths to be used on the HF bands. And that's about all I'll have to say about that. Digital voice versus digital text. I'm going to be talking mostly about text and data modes and not digital voice modes. Digital text modes have to use the CW and data band segments of the HF bands. Digital voice modes and slow scan television must use the voice band segment. That's kind of an arbitrary rule by the FCC, but digitized voice and digitized images are treated as voice, and everything else that starts as data is used in the CW part of the of each band. And I want to talk just for a minute. Some people will say, well, CW, Morse code, in other words, is also a digital mode. And I'm going to wave my hands at that and say maybe, because Morse code is decades older than any digital mode. And strictly speaking, is not encoded as bits. It's encoded as dits and das, which are different lengths, and spaces are important too. So you can say that CW is sort of kind of a digital mode, but you can also say it's sort of kind of not quite. Another reason is CW is the only mode that basically keys your transmitter on and off. The other modes we talk about don't do that. So what makes something a digital mode? First of all is the data protocol. that's used to encode the data and to decode and interpret it. And there's the method of modulating the data onto an RF carrier. So I want to talk about optimization. There are a whole bunch of digital modes because they're optimized for different things. Some things you can optimize for are speed, reliability in noisy or fading conditions, efficient use of bandwidth, error-free transmission, and success in overall difficult conditions where you get noise and fading and interference and so forth. But you can't optimize for all of those things at once. So there are always trade-offs, and some digital protocols, digital modes are better, excuse me, in some situations than others. So where have we got on digital modes? Well, to give you an idea, back in 1980, this is on the left is what radio teletype looked like. You had an audio interface unit that you hooked to your radio, and on the other side, it hooked to a real teletype machine, and that's about what teletypes looked like in the 1980s. If you watch if you watch old movies where that take place in at newspapers, you'll hear teletypes clattering in the background, and they are bigger and not as clean looking, and those are definitely older. But anyway, that's a teletype from 1980. And then on the right-hand side, fast forward to today, and you're looking at a piece of software that runs on your home computer that talks to your radio through a sound card interface. And what a typical setup looks like is um, in the lower center, you've got your radio, which is connected to an antenna on the right-hand side. So that's the radio part of it. On the lower left, you have a you have an interface between your computer and the radio. It's a sound card more or less, but it also has a way to control the push to talk of your rig. In other words, to switch between transmit and receive modes. And then on the upper left is a computer, and that's used to both encode and decode the digital signals as audio. So the computer is connected to it sends digital audio to the audio interface box by USB cable, and then the audio interface is connected to the radio. Now, also, if you have what's called cat control, where you can tell what the radio frequency, what the frequency of the rig is, and so forth, there can be another radio control cable that doesn't directly control digital mode operation. And then also, new radios made in the past few years have a computer have a audio interface built in. So what you'll see with newer rigs, and pretty much anything that you buy new these days, is computer control and computer audio go by a USB cable directly to the radio, and there's no extra box to use digital modes. So the other part of this is you're going to be using software. You're going to be using software on your home computer to interpret to interpret the uh, uh, digital data that's carried via radio. And this is FL Digi, and I think I don't know if this is radio teletype or if this is PSK 31. And I'm going to talk about both of these probably next week at the rate we're going here. But what you can see here is on along the top is information about the radio, and information toward the right here is information about the call sign, well, about the station that you're talking to, or the station that you're listening to, depending. On the left-hand side here, you can see that the software is interpreting multiple signals. And there are different conversations going on, and it is telling you what's going on in all of them. In the uh, in the upper right here is the particular conversation you want to be listening to, and then along the bottom here, you can see a waterfall display, and I'll talk about and demonstrate waterfall displays next week. But that gives you an idea of where the various signals are. And it's called a waterfall because it sort of scrolls downwards. So the newest signals in time are at the top of that window, and then left to right are different frequencies. And you can see that this just covers a very narrow range of frequencies, about 3 kilohertz, or in other words, about the audio bandwidth of a rig. And I'll also get into that next week. So the two most popular programs for digital mode are the two most popular units of software are FLDigi, which handles a whole bunch of different uh, modes, including particularly radio teletype and PSK 31, PSK 63, which are the second and third most common or most popular modes, but also a lot of other stuff. And then WSJTX is the other one that's popular, and that handles FT8 and so-called weak signal modes. Some of those are intended for very weak signals, things that you can't even hear with your ears. Some of them are for things like bouncing signals off the moon. But the idea is weak signal modes are designed to work with very weak signals that are often too weak to hear by ear. But now all of these use digital signal processing, which is why they run on your computer. Some new radios have the ability to decode different modes like CW, radio teletype, FT8, but that's not too common yet. So digital modes think computer, audio interface, and radio all together to make this work. Now, it is 13 minutes past the hour, so I'm going to stop here. And next week we will get into, next week we will get into all the details of the official slides. Excuse me. So all the things I've talked about so far might help you understand Chapter 6 better. And then next week I will go through the slides for Chapter 6, and then John and I will arm wrestle to decide who gets to start on Chapter 4, which is the first part of that is the first part, which includes different units that we use, talks about decibels. So I would say have a scientific calculator handy for next week. And if you don't own one, in order to use one on the test, you'll have to get a separate calculator that will do at least logarithms and powers of 10. So that's usually a scientific calculator, but it can't be a memory calculator or a graphing calculator. And in the exam, you can't use the calculator on your cell phone. So my advice is to actually go look at the dollar store where they often have them. I bought one for a couple of bucks a few years ago, and when the battery eventually runs down, I'm just going to throw it away because it was so cheap. But that's an easy way to do things. So with that, I am going to say We are done for the evening. Are there any questions?